Your interviewer asks, where would you scale this system? You start drawing boxes on the whiteboard, app servers, databases, load balancers. Then they stop you. Wait, what's actually inside one of those boxes? And you freeze. Because for 2 years you have been writing code that runs on the server. You have deployed to the server. But if I ask you right now, what is server physically? Could you actually answer? Here's the secret. A server is just a computer. Same parts as your laptop. CPU, RAM, disk, network card. That's it. And every scaling decision you will ever make traces back to one of those 4 parts. By the end of this video, you will know exactly what's inside the box and you will never look at a system design problem the same way again. Let's get into it. A server is a computer. That's it. The dramatic version is it's a computer that runs your code, sits in the building somewhere and wait for someone to ask it for something. But it is still fundamentally just a computer. The only real difference between a server and your laptop is that it spends its time doing. Your laptop opens a browser. A server opens a network port and listens. Your laptop has a screen. A server has no screen. But the parts are identical. Both have CPU, both have RAM, both have disk, both have network card. 4 parts. Same 4 parts always. So when you hear someone say we need a bigger server, they are not talking about a magic black box. They are saying one specific thing. They want more of at least one of those 4 parts. Stick this in your brain forever. A server is just a computer with 4 parts that you can run out of: CPU, RAM, disk, network. That's the whole story. If you understand those 4 resources, how they fail, system design becomes 10 times easier. Because the server is slow conversation is really a conversation about one of those 4. Let's picture a server as a restaurant kitchen. Once you see this, you will never forget which part does what. The CPU is a chef. A chef does the actual cooking. Every dish, every web request, every database query, every line of your code passes through the chef's hands. The faster chef finishes dishes faster. A second chef means 2 dishes at once. But a single chef can only chop so fast. The RAM is a prep counter. Right next to the chef, bowls of chopped onions, marinated chicken, sliced tomatoes, everything the chef needs right now within arm's reach. The prep counter is fast. The prep counter is also small. Put more than fits and you start losing time looking for ingredients. The disk is the walk-in freezer, huge, hold 100 times more food than the prep counter. But every time the chef needs something from the freezer, they have to stop, walk across the kitchen, find it, walk back. A trip occasionally is fine. 100 trips a minute and the kitchen grinds to a halt. The network card is the waiters. Waiters bring orders in from customers and carry finished plate out. If the waiters are slow, customers wait. Too few waiters, finished plates pile up at the pass. A slow kitchen could be any one of these. Maybe the chef is overwhelmed. Maybe the prep counter is full. Maybe they are sprinting to the freezer every 2 seconds. Maybe the waiters are stuck at the door. Same kitchen, 4 different ways to be slow. Your job as an architect is to figure out which one. There are 3 reasons every engineer need to know what's inside the server. Reason 1. Every scaling decision is really a which of the 4 decision. When your boss says we need to scale up, senior engineer don't say yes or no. They say scale up which resource? Are we out of CPU, out of memory, disk, network? Pick wrong and you spend money while the system stays still slow. Reason 2. Every cloud bill is a bet on these 4 parts. When you pick an AWS instance type, you are buying a specific mix of these four resources. A compute optimized instance gives you lots of CPU, less RAM. A memory optimized instance flips it. Pick the wrong shape and you pay double for half the performance. Reason 3. Every production incident is one of these four running out. The site is slow. Okay, but which resource is exhausted? This single question asked early is what separates engineers who debug fast from engineers who guess for 3 hours. Once you have the four parts in your hand, system design stops being abstract. It becomes concrete. It becomes a resource problem you can actually count. Here is where we are going. Each of the four parts has a different speed, different role. Knowing their numbers, even roughly, is what makes you sound senior in the system design interview. Start with the CPU. A modern server CPU runs at a few billion cycles per second with anywhere from 4 to 96 cores. Each core can do one thing at a time. So a 16 core server can, in theory, do 16 things in parallel. Real code rarely uses every core perfectly. The CPU is your compute budget. If your code is slow because it's doing heavy math, image processing, video encoding, you are CPU bound. Next is RAM, your memory. A typical server has anywhere from 16 GB to 256 GB of RAM. It is incredibly fast. Reading from RAM takes nanoseconds. Compare that to reading from disk, which takes thousands of times longer. This is why caching exists. Move data from disk to RAM and it's 100 times faster. The catch: RAM is small, and when it fills up, the operating system starts swapping data back to the disk. Your fast system becomes a slow one almost instantly. Then comes the disk. Disk is a permanent storage. Even when the server reboots, the data stays. Two main kinds: spinning hard drives, cheap and slow. The solid state drives, SSDs, faster but more expensive. A read from a hard drive takes 5 to 10 milliseconds and SSD read takes 100 microseconds. A RAM read takes 100 nanoseconds. Each step is roughly 100 times faster than the next. Finally, the network card. This is your link to the rest of the world. Speed range from 1 GB per second on small server to 100 GB per second on big ones. Even a perfectly fast server can't beat the speed of light. If you are serving big videos or chatting with 20 microservices per request, you are network bound. Look at the diagnosis table. CPU pinned at 100%. You are compute bound. Memory swapping or out of memory errors. You are memory bound. Disk reads queuing up. You are disk bound. Bandwidth max with packet loss. You are network bound. Every scaling problem fits into one of these four rows. I want to be honest with you about something most courses won't tell you. The good news: this mental model, server equals 4 resources, is the cleanest framework in the system design. You can apply it to a laptop, a bare metal server, a cloud VM, a Kubernetes pod, or a serverless function. The parts are always the same. The bad news: real life is messier. Sometimes 2 of the 4 are bottlenecked at once. Sometimes the bottleneck moves. You fix CPU and suddenly disk is the new problem. You have to measure, not guess. And here is what people get wrong. They reach for, we need a bigger server before measuring anything. That's not engineering. That's a panic with the credit card. Always measure first, then decide. 4 questions you should be able to answer after this video. Question 1. What are the 4 main resources of server? CPU, RAM, disk and network. CPU does the work. RAM holds data fast and temporarily. Disk holds data persistently and slowly. Network connects the server to everything else. Question 2 is, why is RAM so much faster than disk? Because RAM is electrical and disk is a mechanical or a flash based. Reading from RAM takes around 100 nanoseconds. Reading from an SSD takes 100 microseconds roughly. 1,000 times slower. Reading from spinning disk is another 50 times slower than that. Question 3. What does it mean for a service to be a CPU bound or IO bound? A CPU bound service spends most of its time computing. Its CPUs are the limits. An IO bound service spends most of its time waiting on disk or network. Adding CPUs help the first. Caching or faster disks help the second. Question 4. If your server is slow, how do you figure out which resource is the bottleneck? Run a tool that shows resource usage. Look at the CPU percentage, memory percent, disk reads per second, and network throughput. Whichever one is P near its limit is your bottleneck. Don't guess, look. That last one alone will save you in the interview. Before you go, take 30 seconds to log this in. Takeaway 1. A server is just a computer. CPU, RAM, disk, network card. 4 parts, same as your laptop. Takeaway 2. The server is slow problem is exactly one of those 4 running out. Your job is to figure out which one. Takeaway 3. Each part has a wildly different speed. RAM is roughly 100 times faster than SSD, which is roughly 50 times faster than spinning disk. These ratios are why caching exists. In the next video, we will get into vertical and horizontal scaling, what it actually means to add more servers. If this helped you, hit subscribe so you don't miss the next one. The full system design playlist is linked below. See you in the next video.